Hey everyone, welcome to Descriptive Chem slash Lab Part 1, where today we're going to go over precipitation reactions, solubility rules, and gas evolution. Before getting into precipitation reactions, we should go over the 5 types of reactions. So there are a lot of reactions in the universe, but a lot of them can be summed up in these 5 categories. So synthesis slash combination, decomposition, combustion, single displacement, and double displacement. Let's start with synthesis slash combination reactions. And they're in the general form A plus B produces AB. So A and B could be elements, so carbon and oxygen produce carbon dioxide, or they can be compounds like water and sulfur trioxide to produce H2SO4, or water and carbon dioxide to produce carbonic acid. And interestingly, these two compounds are results of why rain is acidic. So SO3 is a major pollutant, and when it reacts with the water falling from the atmosphere, you have that acid rain. But naturally, you have carbon dioxide as well. So the carbon dioxide in the atmosphere reacts with the water and creates carbonic acid, and that makes rain naturally acidic. At this point, you might be wondering why the O2 here has a subscript of 2, and that's because oxygen is a diatomic element. And diatomic elements are elements that occur naturally as pairs. So in the atmosphere, you don't see single atoms of oxygen, you see them coming in pairs. And that is a fundamental idea of diatomic elements. And there are going to be 7 of them: hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And people come up with interesting ways to memorize them. And one of the acronyms is, or the mnemonics is, have no fear of ice cold beer. If it helps you remember it, then great. But what you need to know are that these elements are diatomic, meaning they come in pairs, and you're not going to find them naturally on their own in their monatomic form. Another interesting thing about these is that hydrogen, nitrogen, fluorine, and chlorine are going to be gases at room temperature. Bromine's a liquid, and then iodine can be liquid or solid. But really, the important thing is the hydrogen, nitrogen, fluorine, oxygen, chlorine, and to know that they're gases at room temperature. All right, let's do an example. So we have H2 and O2, and you would think that produces H2O2, but that is incorrect. And the reason why is because the compound that we form needs to have a net charge of 0. So if we look at ionic charges, hydrogen has a +1 charge, and oxygen has a -2 charge. You can tell from the table here. So H2O2 is going to have a net charge of -2. And we cannot have that. The compounds we form must have net charges of 0. So what would it really be? Well, we know that it's going to be H2 and O2 to produce some combination of H and O. That is the point of a combination reaction. And since hydrogen has a +1 charge and oxygen has a -2 charge, a combination that works is H2 and then O just 1. And that produces a net charge of 0. But you might notice from this is that it's not really balanced, right? You have 1 oxygen on the right-hand side and 2 on the left. So if we balance it, it comes out to about like this. A common trend you might see while I'm going through this is that a lot of the reactions aren't balanced, and that is just for simplicity's sake. Something you might be wondering is that why are they ionic charges for things that aren't ionic compounds? And the answer to that is that they're not really ionic charges. They're oxidation numbers, but I don't want to get into redox reactions right now. So for now, just think of them as charges on these elements, and then the compounds that you form must have a net charge of 0 unless otherwise stated. Let's move on to the next type, which is decomposition. And it's basically the opposite of a synthesis, where we go from AB to A and B. And so again, you could have elements or compounds. Like this reaction right here is the opposite of what we saw in the example that we did. So we're breaking down water into hydrogen and oxygen. And then over here, we're breaking down calcium hydroxide into calcium oxide and water. Decomposition reactions are pretty simple, and they're easy to identify But what's even more easy to identify is a combustion reaction. In a combustion reaction, you have some compound A that reacts with oxygen to produce carbon dioxide and water. A is usually a hydrocarbon, and a hydrocarbon is just something that's in the form of C and H. So whatever subscript you have there, but it must be a form of C and H. And I say usually because sometimes you see combustion reactions happening with compounds including oxygen in the mix or some other types sometimes, but usually it's a hydrocarbon. Like the first example here, we have methane plus oxygen produces carbon dioxide and water. And the next one is like one of those exceptions where they include oxygen in there. And but really, it's still easy to identify because you have it reacting with oxygen to produce carbon dioxide and water. And that is a single displacement reaction. And these reactions are in the form A plus BC produces B plus AC. And remember, the AC that we produce needs to have a net charge of 0. And that means we have two possibilities for what A can be. So if A is a cation, implying that we have a positive charge, then that means that the positive charge is going to react with the negative charge. And the negative charge here is the chloride. And so zinc reacts with chloride and copper gets left on its own. The other possibility is if we have an anion, something like bromine, and bromine is going to have a negative charge. And in order for the compound that we form on the right-hand side to be neutral, the bromine must react with the cation. So negative charge, positive charge. And the positive charge in this case is the K, or the potassium. And that's why we form potassium bromide and not something like bromide iodine. That doesn't even make sense. You can also see here that when we did make the potassium bromide, the bromide went from a 2 subscript here to a 1 subscript here, and that's because potassium has a +1 charge and bromine has a -1 charge. So in order to balance out the charges, you only need one of each. You don't need two, like we have, and so that's why you have the balancing of the chemical equations here with the 2. The last type of chemical reaction that we are going to discuss is a double displacement. And double displacement is where the reactants AB plus CD produce AD plus CB. You can think of it like wife swap if you've ever seen that. And so A and C here are the cations and B and D are the anions. And that means that AB, CD, AD, and CB are all neutral. And that is very important. So let's take a look at this example right here. We should first write down all the charges of these elements. So barium is going to have a +2 charge. Chlorine is going to have a -1 charge. Silver here is going to have a +1 charge, sorry. And NO3 here is going to have a -1 charge. The Ag here, the reason we know that it has a +1 charge is because we know that the polyatomic ion here, nitrate, has a -1 charge. And so in order for this compound here, AgNO3, to be neutral, we know that Ag must have a +1 charge. All right, now let's do the double displacement. So Ad, the barium is the A, and the D is the nitrate. And since barium has a +2 charge and nitrate has a -1 charge, it's going to be in the form of barium nitrate 2. And Cb. C is the Ag here, and the B is the chloride here. And since they both have a -1 charge and a +1 charge, that means you only need one of each to balance out the charges. And so I don't think this is balanced, but that is the double displacement reaction complete, basically. Again, the charges here are really important to determine the subscripts. You need to make sure that all the compounds involved have a net charge of 0, unless, of course, otherwise stated. Let's go through one more example before moving on, because double displacement reactions are actually kind of really important. We have calcium carbonate plus hydrochloric acid. So calcium is going to have a +2 charge, carbonate has a -2 charge, hydrogen has a +1 charge, and chloride has a - charge. So in order to make Ad, we know that the calcium here is the A, and then the D is the chloride here, And so it's got to be calcium chloride 2 in order to balance out the charges. And it's going to be plus Cb. So C is the hydrogen, B is the carbonate. And in order to balance that, we have H2CO3. And that is the double displacement reaction basically complete. Again, I don't think the equations are balanced, but I wouldn't worry too much about that since they're pretty simple to do. The important part, though, is the balancing of the charges again. There are three types of double displacement reactions that are really important, and they're acid-base neutralization, precipitation reactions, and gas evolution reactions. And we're going to go through all of them, starting with the acid-base neutralization reactions. They are in the general form of an acid and a base reacting to produce a salt and water. And this lets us define a salt. A salt is an ionic compound that results from an acid-base neutralization reaction. So let's look at the formation of a very common salt. And so we have hydrochloric acid plus sodium hydroxide. And what does that produce? Well, we know it's a double displacement reaction, so let's do that double displacement reaction. Hydrogen has a +1 charge, chlorine has a -1 charge, Na has a +1 charge, and hydroxide has a -1 charge. And so Ad is H2O, and Cb is NaCl. What we just created here is NaCl, or table salt, and this is the reaction that's used to make table salt. So again, an acid-base neutralization reaction, taking an acid, in this case we had hydrochloric acid, base, the sodium hydroxide, and we created a salt, NaCl, and some water. The next double displacement reaction that we're going to look at are precipitation reactions. And I want you to take a look at this reaction right here, where we're taking aqueous AgNO3 and aqueous MgCl2, and aqueous just means that they're dissolved in water, of course, and that produces, obviously, something aqueous. You get that, you do that double displacement reaction, you get something aqueous, but interestingly, the second bit that we get is a solid. That's symbolized by the S right here. And so how did we create a solid from two aqueous reactants? These types of reactions are called precipitation reactions. So it's a reaction in which two aqueous solutions are combined to form an insoluble salt. And the insoluble salt, we call that the precipitate. So in this case, we took two of these aqueous solutions and we combined them to make the precipitate AgCl. Now this is interesting, but how do you know that something is soluble or not? So if I were to just give you this equation without giving you the product side, could you be able to tell me that AgCl would have, one, resulted, and two, been a solid? And that is yes. These are your general solubility rules. And this is one that I made because I found that a lot of the ones online didn't have a lot of the stuff that's covered on the test, because on the test, they're not going to ask you about the normal stuff. They're going to ask you about the weird exceptions. And a lot of the tables online didn't have the exceptions. But basically, a general solubility rule tells you whether a compound is going to be soluble or not. And so let's look at what that looks like. If we look at something like tin sulfate, you can see from this section here that all sulfates are soluble unless they are with barium, lead, calcium, or strontium. And tin is not one of those exceptions, and therefore it must be soluble. And we see that's true. Let's take a look at the next one, strontium chlorate. Chlorate here is always soluble, and there are no exceptions. So it is always soluble. That means obviously strontium chlorate must be soluble. Next one, silver bromide. So bromide is right here. Bromide is always soluble unless it's with silver, lead, or mercury. And we have silver bromide. And so that triggers the exception right here. And that means silver bromide is insoluble. Last one, copper carbonate. Carbonate is right here. And it's always insoluble unless it's with a group 1 ion or NH4. Copper is not a group 1 ion, and nor is it NH4. And so that means copper carbonate must be insoluble. And that's what we see here. A solubility rules table is very helpful because if you can just look at a compound and you could tell with pretty good certainty whether or not it's going to be soluble or insoluble, but they don't give a solubility table on the test. So you are going to have to memorize these, and they're honestly not too bad to memorize because once you do some practice, you get like an intuition for it, just like with a lot of other things in chemistry. And let's do a bit more practice using questions that are from actual tests. Which combination of dilute aqueous reagents will not produce a precipitate? All right, and we have a bunch of options, and let's go through each one of them. Let's first take a look at silver nitrate and hydrochloric acid. So if we do the double displacement reaction, we're going to get that it's going to be AgCl plus HNO3. And now we can use the precipitation dissolubility rules to see if we're going to form a precipitate. Right off the bat, you can tell here from the chloride here, chloride is always soluble unless it's with silver, lead, or mercury, and we have silver right here. So that means this AgCl right here is going to be a solid, and therefore that means we do produce a precipitate, meaning A can't be the right answer. Let's take a look at the next one, NaOH plus HClO4. If we do the double displacement reaction, that's going to give us NaClO4 plus H2O. Well, obviously the H2O here is not a precipitate, it's water, right? But the NaClO4, we need to check that. So we have Na, and Na is a group 1 ion, and they're always soluble, meaning NaClO4 is going to be aqueous, and so is the water, meaning there is no precipitate here, and so B has to be the right answer, but let's go over C and D anyways. C is barium, Br2, plus Na2SO4, and so the double displacement reaction gets us to BaSO4 and NaBr. The NaBr here we know is going to be aqueous. That's always soluble. But the barium sulfate, let's take a look at that. Sulfates are always soluble unless they're with barium, lead, calcium, or strontium, and we have one of those exceptions. We have barium. And so that means this is going to be a precipitate, it's going to be solid, and therefore C is obviously not the right answer. Last one, zinc iodine plus potassium hydroxide. The double displacement reaction comes out to zinc hydroxide 2 plus Ki. Okay, so iodine is always soluble unless it's with AgPb or Hg, and those are not, potassium is not one of them, so Ki is soluble. Let's take a look at zinc hydroxide. We have rules for hydroxide here, and hydroxide is always insoluble unless it's with a group 1 ion, strontium, barium, boron, and calcium is somewhat soluble, but zinc is not one of those exceptions. And that means that zinc hydroxide is a solid, and that means that it produces a precipitate, and D is not the right answer. And as we determined, B is going to be the right answer. And we are correct. Let's move on to gas evolution reactions. So you might have done this experiment when you were younger, where you take baking soda and vinegar, and you put a balloon over it, and the balloon blows up. And let's take a deep look at what's really going on chemically. So we have vinegar, which is acetic acid, and baking soda, which is sodium bicarbonate, and we are putting that in a chemical formula. So you have your typical double displacement reaction, and the products that you produce, you don't have a precipitate in it. You can tell with solubility rules that you're not going to have a precipitate in it, but there's a weird thing about this reaction. Where is the gas coming from? There is gas in this balloon, but in the chemical equation, all we see are aqueous substances. Well, turns out that the H2CO3 is an intermediate, meaning although it is formed and it stays there for a certain period of time, eventually it breaks down into other substances. In this case, carbon dioxide and water. And so just how H2CO3 is an intermediate, we're going to have a couple more. H2SO3, NH4OH, and H2S. So if you see any of these products, then that means you are going to have a gas evolution because they are intermediates and eventually they break down into gases. And so a gas evolution reaction is a reaction that produces one of these intermediates. Let's take a look at an example to further understand this. Addition of 6 molar hydrochloric acid to which substance will not result in gas evolution? So let's go through all the answer choices, starting with aluminum. So aluminum plus hydrochloric acid, that's your typical single displacement reaction. So you're going to have AlCl3 plus H. But remember, H doesn't exist on its own. It's one of those diatomic elements. And that tells us that the H2 is a gas. So remember I said those of those diatomic elements, a lot of them are going to be gases. Hydrogen is one of them. And so although it doesn't look like we have an intermediate, we have hydrogen, which is a gas in itself. The next one is zinc. And we're going to have zinc plus HCl. And we know it's going to produce something, but really what we're looking at is the fact that hydrogen is going to be on its own again. It's very similar to the Al that we just did. And again, there's going to be a gas evolution because at the end, you're going to have hydrogen on its own, and that is a gas. So the first two cannot be the answer. Let's take a look at the third one. So K2CO3 plus HCl. Typical double displacement reaction, so let's do that really quickly. We're going to have KCl plus H2CO3. And look at that, we have one of our intermediates. And H2CO3 is going to break up into CO2 and H2O. And the CO2 here is a gas. And so that means if you were to react K2CO3 with hydrochloric acid, you are going to have a gas evolution. And so C cannot be the answer. By default, D has to be the answer, but let's take a look at why. So we have NaNO3, and we're reacting NaNO3 with hydrochloric acid, and that's going to form NaCl and HNO3. Well, take a look at that. These are not intermediates. None of these are intermediates, and these are not going to result in a gas evolution. We don't have any of those diatomic molecules, we don't have any intermediates, and this has to be a non-gas evolution. So the answer is D. And we are correct. Alright, so let's do a bit of practice using all the information that we learned to do these 3 practice problems. The problem asks, addition of small amount of which solid to 4 molar hydrochloric acid will result in gas evolution. And we have 1 and 2. So let's do the thing. And coincidentally, we literally just did this. We know that something's going to form, but really what we care about is the hydrogen here. Hydrogen's going to be left on its own, and it's a diatomic molecule, and it is a gas in its room temp at its standard state. And therefore, we are going to have a gas evolution if you react zinc with hydrochloric acid. So 1 is going to work. Let's take a look at 2. Na2SO3. If you react that with hydrochloric acid, again, it's going to be very similar to the one that we just did. We're going to have NaCl plus H2SO3. Sorry. And H2SO3 is one of those intermediates, and this is going to turn into a gas, and we are going to have a gas evolution. So 2 also works. And therefore, the answer must be I and 1 and 2. Sorry. And we are correct, either 1 or 2. Next up, a 2 milliliter sample of a colorless solution, when treated with a few drops of 2 molar hydrochloric acid, forms a white precipitate which dissolves when the solution is heated to boiling. The original solution could have contained which of the following cations? This problem is one of the reasons why I recommend using the chart that I made instead of other charts online, because you'll see why we're going to run into a problem if we use some other chart. So let's look at one, Ag, and we have HCl. So that's going to produce AgCl and hydrogen. Well, we know it's going to contain Ag, so hydrogen plus something else, whatever. But what we really care about is the AgCl right here. And AgCl from our solubility rules is going to be insoluble. Ag is one of those exceptions right here. And that means we are going to form a precipitate. But before we jump to conclusions, let's look at the second one too. Pb2 plus something else plus HCl is going to produce Pb2Cl plus H something. Again, Pb2Cl is going to be a solid. It's one of those exceptions. But where this question tricks you up is at this point you might be thinking, okay, it could be one or two, but we need to consider the additional information. We are told that it dissolves when the solution is heated to boiling. Ag is a normal precipitate. It's going to stay solid whether or not you heat it up much or not. But Pb here is only slightly soluble in cold water, but it is moderately soluble in warm water. So if you were to increase the solution to boiling, then the Pb would eventually dissolve. And that is why the only right answer is 2. Because 1 does not satisfy this part of the question. Only the lead will satisfy that part of the question, and therefore the only right answer is 2. And that is our answer. Let's take a look at the last one. An aqueous solution contains the ions Ag, Ba, and Ni. Dilute aqueous solutions of NaCl, Na2S, and Na2SO4 are available. In what order should these solutions be added if the goal is to precipitate each of the 3 cations separately? In order to solve this problem, let's take a look at the precipitating agent, per se, of the dilute solutions. So in NaCl, it's going to be the chloride, because it's going to be the chloride that's going to mix in with these cations. In Na2S, it's going to be the sulfur. And in Na2SO4, it's going to be the sulfate. And let's take a look at the solubility rules for chloride, sulfur, and sulfate. For chlorine, they're all going to be soluble unless they're silver, lead, or mercury, and we have silver. So that means silver will precipitate if we put NaCl into the aqueous solution with the cations. The next one, the S, the sulfide here is always insoluble unless it's with a group 1 ion, NH4, and calcium, barium, and strontium are somewhat soluble. But of those, we have barium, and so barium is the only one that's not going to precipitate, right? Because all the others are going to be insoluble, but barium is one of those exceptions. So the ones that can precipitate are going to be the Ag and the nickel. For the last one, let's look at the solubility rules for sulfates. Sulfates are always soluble unless they're with barium, lead, calcium, or strontium, and we have one of those. We have barium. So it's going to precipitate the barium. So the order that we can go to precipitate these one at a time is if we did NaCl first, and then Na2SO4 second and third, we could first precipitate off the Ag and then the barium, and then since there's no nickel in the solution, there's no silver in the solution, we can precipitate the Ni last. And so the order is going to be NaCl, Na2SO4, and Na2S, and that is D. And we are correct. That's all I have for this lesson. I hope you learned something, and I'll see you later for part 2 of Descriptive Chemistry / Lab.